Hi everyone, my name is Eric Trotman and I'm a first year PhD student at the University of Florida in the Kaiser Lab. And today I'm going to talk to you about the phenotype as plasticity and the carryover effects across life stage trade-offs in predation and parasitism. This is a conceptual talk about my dissertation ideas, so I'd love any comments or thoughts afterwards. Okay, so inducible antidiuretic defenses have been described in many different taxa. These antidiuretic predator defenses exist under the umbrella of phenotypic plasticity, which often exists in the form of inducible defenses, which function to combat risky environmental conditions. So in the well-studied safe of the Daphnia, these species are known to change their morphology in specific environments containing certain predators. So on the far left, we have the normal morphology of a Daphnia, and then the next two images are of Daphnia that have been raised in the presence of certain predators, and they've developed these morphologies such as this armor plating and this spike to evade such predations. So this sort of morphological change is known as an inducible anti-predator defense, and they're often permanent changes in morphology or physiology that can then alter behavior and reduce mortality risk in the presence of predators. But this also occurs in individuals that have multiple life stages, such as amphibians, which is the focal species for my dissertation, and these are known to change their morphology in the presence of gate-limiting predators and have a bigger head-to-tail body ratio. So this is just a flow of concepts today. So we'll talk about phenotypic plasticity, going to the inducible defenses across the lines of morphology, physiology, and behavior, look into carryover effects, how they can be concordant or antagonistic, and then like how we can use those fitness effects that caused by carryover effects to help with conservation initiatives of amphibians. So inducible defenses are costly, which means that they can incur trade-offs within a life stage of an individual. This is that responding to a specific predation or parasite cue, such as a chiromone, may be costly in other contexts within that life stage. So such as the Pacific tree frog, an experiment was done where it was found that tadpoles reduced their activity in the presence of caged predatory dragonfly larvae, but which then led to an increase in trematode infection load because they had reduced their movement. Larval boston newts that were housed in dark, low-reflecting microhabitats increased their skin pigmentation, which led to a metabolic cost trade-off of increased oxygen consumption. So carryover effects have long been known due to the hypothesis of the clean state hypothesis. It's long been proposed that individuals that have multiple life stages, evolution acts independently on each of those life stages who undergo metamorphosis. However, in the past 20 years, many studies have been done to document the existence of carryover effects and somewhat go against this hypothesis of the clean height hypothesis. So a study by Moore and Martin found that carryover effects can be showed in two different ways. One is colloquially known as the silver spoon effect, meaning that environmental circumstances in one life stage set them up for success at every life stage. So this means they have concordant fitness events. So whatever happens to them in their early life stage doesn't have a cost in their later life. But the other way is with the ontogenistic conflict, when carrier effects have different level of performances across life stages, is said to have an antagonistic fitness effect. So we'll get into a little bit about that further. But first, I'm going to talk to you about behavioral syndromes now. So behavioral syndromes, although they're not typically known as phenotypic plasticity, these predict that individual behavioral traits should be maintained throughout life history. They may help maintain individual variation in behavioral type and can potentially explain non-adaptive behaviors in isolated contexts. So in the case of the spotted salamander larva, it was showed across all these axes of behavior, across activity, boldness, and exploration, and these are ways that they've measured them, that across all three behaviors, these activities were positively correlated, meaning that more active and bolder and exploratory larvae then became bolder subadults post-metamorphosis. So this is a simple about how these behavioral syndromes can actually carry over across life stages and potentially have this carryover effect like we talked about beforehand. So under what circumstances do trade-offs between predator defenses and immunity carry over to future life stages? So we'll get into this. And a reason why I study this is because it's not well studied in amphibians, but I'll give you a couple of examples with other systems. So these carryover effects are what I'm referring to as behavioral, morphological, and physiological changes developed in one stage, providing defense against enemies at that stage, but potentially leaving individuals at disadvantage in subsequent life stages. So for one example is within the juvenile Trinidadian guppies. So these guppies are shown to show a behavioral trait of shoaling behavior regardless of predation pressure. However, as they get into adulthood, adult female guppies continue this behavior only in high predation areas. But what this means is that their closer relationship with one another in this shoaling leads to higher infection rates of ectoparasites transferred from one to the other on females. Males in these populations who don't display these shoaling behaviors have lower levels of ectoparasites found within them. In the case of brush-legged wolf spiders, it was found that in the juvenile stage, immune activation resulted in a higher immune response as adults compared to controlled individuals. And what they did was that they infected individuals with disease, and then they left them off into adulthood. This led to a lower body condition and a higher degree of asymmetry in four-legged tufts as well, meaning that infected males had a relatively smaller tufts than controlled males. So this gets at that trade-off between sexual reproduction and fitness and immune response to disease in their environment. So amphibians also are able to change their morphology, behavioral, and physiology in the presence of predators or parasites. One such example is with predators. Certain amphibians, like we saw, reduce their activity, but they can also cause deeper tail fins and stronger tail muscles to avoid predation. They're also been shown to decrease antimicrobial peptides during specific conditions, when they have to change their morphological. So this is a trade-off that they get off as well in this situation. And this is one case that I found in a lit review that I'll get to later. But within the case of parasite-induced, it's found that in the presence of free-swimming parasites, tadpoles have been shown to have elevated activity levels and display behaviors that are not seen in tadpoles outside of the presence of sweeping parasites. So they do things like body twisting, tail flicking, and burst swimming. So in boxes 5 and 6, you can see this tail flicking behavior, and in 16 and 15 on, you can see this example of like extreme body twisting to evade trematodes from latching onto their body. So animals that undergo metamorphosis provide a really unique opportunity to explore these carryover trade-offs because they have such a plethora of events and adaptivities that they have to avoid in life and be able to adapt to. So this is that exposure to early life events may have prolonged effects throughout life and across life stages. So in the case of tadpoles, this is a limited research that I've done with them so far, but they have enemies from crawfish, trematodes, fishing fighters that live in the water, and they have to be able to adapt to these within that life stage. However, their next life stage takes them, through a very costly time in their life when they're developing their limbs and going through metamorphosis. But they're also now having to adapt to life on land. They also have to now deal with predators that only exist on land, such as snakes and other individuals that can attack them from the land now. And then you would think that through adulthood, they'd finally be done. But no, now they potentially have predators from the air, predators from the land now, and they also have to deal with just environmental conditions, habitat change, many different plethora of things that they have to adapt to. So this is why they really have this unique opportunity to explore these carryover trade-offs across life stages. So in a lit review that I did, this is still in progress, but I explored the literature to identify carryover effects between predators and parasites specifically. And I found direct evidence for within life stage trade-offs in response to predation and parasitism, as well as direct evidence for cross-developmental trade-off within a single context, like I talked about earlier. However, we only found indirect evidence for carryover effects in amphibians, highlighting the need for more experimental tests for this hypothesis. Okay, So I'm going to leave you with this kind of potential carryover effect pathway that I would try to get at exploring through my dissertation. So if we have the case of a tadpole raised in the presence of a trematode or a gate-limiting predator, such as a largemouth bass, like I said before, sometimes tadpoles pick up on the pheromone cues of those predators, and they may increase their head to tail body ratio to escape predation. So they'll grow really quickly, and they'll get to a size where they can no longer be predated by certain predators. However, this increase in surface area now leads them to potentially pick up more parasites later on in life. So if we follow this large tadpole across its life history, we might see that, okay, it might metamorphosize as a larger metamorph, however, with a higher infection load. So this individual might have a harder time making it through metamorphosis, which is a very costly process just without the presence of being heavily infected. However, if this individual does make it through into adulthood, it potentially has a benefit now where it can avoid gate-limited predators such as snakes and certain individuals in the terrestrial stage of life. That's if it can exhibit the defenses against. If we follow the life history of the smaller tadpole that didn't pick up the cues of the predator in the water, and now this might metamorphose as a smaller individual in metamorphic phase, but it might have more energy, or it might be healthier because it hasn't picked up as many parasites as before. However, moving into adulthood, it might not have that added benefit of being a larger individual and escaping predation in that later stage of life. So how does this work for conservation initiatives? So this is a program that I was part of at the San Diego Zoo, where we were looking at the stream experience of the mountain yellowleg frog in the Sierra Nevada range. And we found that stream experience individuals boosted apparent survival for juveniles, but not subadults. But subadults exhibited higher survival overall. And we recommended that captive training practitioners consider a broader array of survival skills and tailor pre-release treatments to specific developmental windows. So thank you for listening. And do you have any questions or thoughts? I'd love to hear from